Good morning, sir. This is Himabindu from CSCA section. Today I am going to explain about generating function sequence in discrete mathematics and graph theory. Introduction to generating functions. Generating functions are formal power series used to represent sequences. They provide a convenient way to manipulate sequences algebraically. Understanding generating functions can simplify problem solving in combinatorics. Definitions of generating function. The generating function is g of x for a sequence a of n is defined as g of x is equals to sum of n is equals to 0 infinity a of n into x power n. This series encodes the information of the sequence in a compact form. We will use this definition to find the g of x for our sequence. Identifying the pattern. Observing the coefficient, they alternate in sign and increase in absolute value. The coefficients seem to follow the pattern minus 1 into x into n minus 1. This can be confirmed for n where a of n equals to minus 1 power x into n plus 1 into n minus 1. Using power series manipulations, we can manipulate the series to extract a useful form. This series can be reformulated using the derivative of a power series. Specifically, we will use sum n is equals to 0 infinity x power n is equals to fract of 1 into 1 minus x. Final form of the generating function is after manipulating we find g of x is equals to fract of x into 1 plus x power into 2. This expression encapsulates the behavior of our sequence. We can now analyze its property further. Verifying the generating function. To verify, we can expand g of x as a power series. Using the binomial series expansion, we find fract of 1 into 1 plus x into 2. Sum is equals to n of 0, n is equals to 0 infinity of n plus 1 into minus 1 into n x power x into n. Thus, multiplying by x results in our original sequence. Generating functions of a sequence. Here let a is equals to n is equals to 0 to up to infinity, where a0, a1, a2 and so on an be the sequence, then its generating function is defined to be a of x is equals to a0 plus a1x plus a2x square plus a3x cube plus and so on an x power n plus and so on is equals to summation n is equals to 0 an x power n. Now note the sequence a of n n is equals to 0 to infinity can also denoted by an a not an or we can denote it as 0 1 an or an or a or r is equals to 0 to infinity or a11 a21 and so on an1 and so on. Imported formulas. 1 by 1 minus x is equals to 1 minus x whole power minus 1 is equals to 1 plus x square plus x cube plus and so on. Here we can write this formula as summation r is equals to 0 to up to infinity x power r. 1 by ax is 1 by a minus x is equals to 1 minus ax whole power minus 1 is equals to 1 plus ax plus a square plus a cube x cube plus and so on. Here we can write this as summation r is equals to 0 to infinity ar into x power r, a power r into x power r. 1 by 1 minus x is equals to 1 plus x whole power minus 1 is equals to 1 minus x plus x square minus x cube plus x power 4 minus and so on. Here we can write this formula as summation r is equals to 0 to up to infinity minus 1 whole power r x power r. 1 by 1 minus x whole square is equals to 1 minus x whole power minus 2. 1 plus 2x plus 3x square plus 4x cube plus and so on. Here we can write this formula as summation r is equals to 0 to up to infinity r plus 1 into x power r. 1 by 1 plus x square is equals to 1 plus x whole power minus 2. 1 minus 2x plus 3x square minus 4x cube plus and so on. Summation r is equals to 0 to up to infinity minus 1 whole power r into r plus 1 into x power r. These are the imported formulas. Now, sixth one, 1 minus x whole power minus n is equals to summation r is equals to 0 to infinity c of n plus r minus 1 comma r into x power n. 1 plus x whole power minus n is equals to summation r is equals to 0 to infinity minus 1 r is minus 1 whole power r c of n plus r minus 1 comma r x power n into x power n. 1 plus x whole power n is equals to summation r is equals to 0 to up to infinity c of n comma r into x power r. 1 minus x whole power n is equals to summation r is equals to 0 to up to infinity minus 1 whole power r c of n comma r x power n. 1 plus 2 plus 3 plus and so on plus n is equals to n into n plus 1 by 2 and 1 plus 2 square plus 3 square plus and so on n square is equals to n into n plus 1 into 2n by 6 1 cube plus 2 cube plus 3 cube plus and so on n cube is equals to n into n plus 1 by 2 into n. Now a plus ar plus ar square plus and so on ar power n minus 1 is equals to a of 1 minus r power n by 1 minus r where r is less than 1 and a is a into r power n minus 1 by r minus 1 where r is greater than 1. 1 plus x square plus and so on x power n is equals to 1 minus x whole power n plus 1 by 1 minus x. E power x is equals to 1 plus x 1 plus x by 1 factorial plus x square by 2 factorial plus x cube by 3 factorial plus and so on. Find the generating function of the following sequence 0, 1, minus 2, 3 and minus 4 given a0 is equals to 0, a1 is equals to 1, a2 is equals to minus 2, a3 is equals to 3, a4 is equals to minus 4. Therefore, the generating function is a of x is equals to a0 plus a1 x plus a2 x square plus a cube a3 x cube plus and so on. Here a0 is 0 plus a1 is 1 and x minus a2 is minus 2 x square plus a3 is 3 x cube minus a3 is minus 4 into x power 4 plus and so on. X into 1 here x common 1 minus x plus 3x square minus 4x cube x into 1 plus x whole into minus 2. Coefficient extraction. The coefficients of the expanded generating function match our original sequence. Specifically, we see the terms 0, 1, minus 2, 3, minus 4 appear. This confirms that our generating function is indeed correct. Applications of generating functions. Generating functions have applications in combinatorial counting. They can also be used to solve recurrence relations. Many problems in probability can be approached using these generating functions. Alternative methods of finding generating functions. Aside from power H series, generating functions can be derived using combinational arguments. Recurrence relation may also provide insight into the form of the generating function. Each method has its own advantages depending on the context. Comparing with the other sequences. Comparing these sequences with others could really reveal interesting patterns. Generating functions can often reveal similarities in behavior. This could lead to a better understanding of the underlying mathematics. Conclusion. Generating functions are powerful tools in mathematics. They allow for efficient manipulating and analysis of sequences. This process of deriving them enhances our understanding of sequences. Thank you, sir.